I'm sure almost everyone has used the built-in filters on modern smartphones. I thought coding a GPU-accelerated image processing algorithm from scratch would be fun. Apple or Google conducts extensive research in image processing. I cannot match that. Also, image processing is not my expertise and I wanted to keep things simple, so I decided to use a simple algorithm called convolution. I wrote a small application that can apply 5 filters to a high-resolution image within a few milliseconds. Let me explain convolution using a simple 1D example where the input is an array of length 5. A filter is defined to compute each element of the output. In this case, I'm going with a filter of length 3. To compute the first output element, the middle element of the filter is aligned with the first input element, and an element-wise multiplication is performed. For the filter element that lies outside the range of the input array, the output is 0. All these intermediate values are then added together and stored as the final output. This goes on for all the elements, and special care is only needed near the boundaries. For image processing, 2D convolution is used a lot. It is the same as 1D convolution, but the input, output, and filters are all 2D arrays. The filter slides over the input elements similarly and computes the output elements. Boundary conditions are a little tricky and handled precisely the same as the 1D case. Applying this algorithm to a high-resolution image is pretty straightforward. Image is essentially a collection of pixels arranged in 2D. For the sequential program, the filter individually slides over the input elements and computes the output image. Modern CPUs are pretty efficient and can do this in a fraction of a second. However, if the application target is live video processing, it might not be enough. Convolution can be parallelized effectively as output elements are independent. The idea is to assign a thread to compute one output element. Each thread loops over the element of the filter matrix and the corresponding input elements, performing multiplication and addition to give the final output. The key is that multiple threads work in parallel, accelerating the whole process. This naive parallelization sped up the program so that it was good enough to cover most applications. However, I wanted to optimize the code using techniques like tiling, which I've discussed in detail in my last video. Looking at the big picture, the input matrix, filter, and output matrix are all stored in the GPU global memory, which is long latency and low bandwidth. Every time a thread needs to perform the calculations, it has to fetch data from the global memory, which takes a long time, and each thread has to do that multiple times. This can be resolved by moving the data or a subset of it to a faster memory unit. Let's start with the filter. Besides global memory, GPUs also have a much faster constant memory unit. The main difference is that it's much smaller and GPU threads can only read from it. This was perfect for the filter because I needed only to read the filter values. With constant memory in use, when the threads perform calculations, they read filter values from here, which is faster than global memory. However, the input matrix is still in the global memory. So let's look at a way to resolve this issue using shared memory. To use shared memory effectively, the output matrix is divided into multiple tiles of the same dimensions. Let's focus on a single tile. An oversized input tile is required to compute the elements of this output tile, and the filter size dictates the size of this input tile. Now, to use the shared memory, one way is to define a block with the number of threads greater than the output tile size but equal to the input tile size. This is done to make copying input tiles to shared memory easy. Note that invalid cell values are set to 0. Once the data is in the shared memory, threads outside the tile bounds can be turned off. The filter is already in the constant memory, so when the threads compute the elements of the output tile, they only access data from shared and constant memory, which in theory should be faster. Comparing the naive implementation against the code using constant and shared memory, there isn't any significant improvement. This was unexpected, so I read more and asked a few questions on forums. It turned out I was missing one crucial thing. So far I have explained the GPU hardware at a very high level. What I never talked about was caches. These are small but fast memory units close to GPU cores. The difference between caches and other memory units is that the hardware automatically manages a cache. Let me explain that using an example. When a thread accesses an element from the global memory, other threads access the adjacent memory units. What happens in a modern GPU is that before delivering the data to the cores, a copy is placed automatically in the cache, Remember that this happens automatically and a programmer does not control any part of it. An upside is that the next time the thread needs a different data point, it can get it from a cache and avoid global memory accesses. This happens for multiple threads and in turn significantly reduces global memory accesses. The next question was, can I do anything else to increase the performance? To see the possibilities, I conducted a thorough benchmarking. Before a GPU gets involved, data is stored in RAM. Moving data from RAM to GPU global memory is an overhead, which is significant compared to the time it takes for the GPU cores to perform the computations. The same applies to moving the results from GPU global memory to RAM. To make a noticeable difference, I must focus on these data transfers. Remember, the CPU can also access slower memory units like SSD. One thing that an operating system does is it manages the RAM by moving the data to and from these slower memory units to RAM. So whenever the program needs to transfer data to the GPU, it might not have been in the RAM. This can slow things down significantly. By the way, this process is known as swapping. As a programmer, I can use pinned memory and instruct the OS not to move the specified data out of RAM. With this minor tweak, the application ran almost twice as fast. The concept of pinned memory is fundamental and is used in several other GPU-related applications. However, that is the topic for some future videos. Putting everything together in one place, it is evident that the naive GPU code can speed up the application significantly. Another interesting thing I learned is that constant or shared memory does not guarantee a speed up. Using pinned memory provided a boost, and learning about it was fun. You can check out the code on GitHub and even use it to apply filters to your own images. I provided support for 5 filters, and the application returns benchmark for every run. As always, please check out the detailed blog post on my website where you can read more about constant memory caches or pinned memory with reference to all the articles that helped me. Thanks a lot for watching. Let me know what you think in the comments, and I will see you next time.